Hi, I'm Jeff Yarger. I'm a professor of chemistry, biochemistry, and physics at Arizona State University. This video is going to cover Chapter 2 in Tinoco's book, Physical Chemistry, Principles and Applications in Biological Sciences, and going to give a general overview of the material covered in this chapter. There'll be subsequent videos with question and answer and working specific screencast problems, etc. This video is really meant just to overview the topic, which is the first law of thermodynamics. And this is something, in a sense, that'll be primarily review because you've covered this in your introductory chemistry and physics courses in the past. And so with the general idea that we'll be looking at it in this book, it gives the applications, though, towards biochemistry and molecular biology type systems. Another book that has been used as well in this course, which is Jim Allen's book, Biophysical Chemistry, covers the same thing in the same chapter. And so these books have been used interchangeably in the past in this course. So I also like to mention that this, in a sense, follows along with this as well. So one of the things that we first need to introduce in thermodynamics is realize that a lot of the terminology we use comes about because of the constraints, or what we'll call the walls of the system. And so we often start by saying we want to look at a specific part of the universe. We'll call that the system. Either the chemical system, the beaker with our material in it, the biological, the cell, whatever, is what we want to look at. And everything else in the universe, it will be the surroundings on it. And it's typically the walls that define between this system and surrounding, as shown here as well, that ultimately dictate a lot about the thermodynamics. So one of the first things we want to do, and first things introduced in Tinoco's book, is talking about whether these walls are open, so whether the system is open to exchanging matter, exchanging heat, etc., or whether they're closed. And then if it's completely closed off from everything, including even heat, we call that an isolated system. I like to provide a table that goes into this a little more detail that really talks about whether a specific variable is either restricted by the walls or not restricted by the walls, and the general thermodynamic terms we talk about here. So if something doesn't allow the flow of heat, like for example, if you put a dewar around something, right, so that heat can't propagate into or out of the system, we call that, where there's no change in heat, where the change in heat is zero, we call that adiabatic. And if we allow the exchange of heat, we call it diathermal, right? If instead of the heat, we just restrict temperature in this, we call that isothermal, and we still call this diathermal as well. So if we close it off to matter, as shown here, where a particle can't go out or other particles can't come in, or what I would say is the derivative with respect to the number of moles is zero, the total and each individual component, then we call that a closed system. And if we allow matter to exchange, as shown here, then we call it an open system. If we block off a system, say with a semi-permeable membrane where we allow, say, for example, red particles to travel back and forth between this. So it's semi-permeable to red, but say not to blue, etc. That's called semi-permeable with respect to specific components within the total number of moles, and otherwise it's open. If we fix the volume by making it a hard walled container, we call that isochoric, where the change in volume is equal to zero. If we allow flexible, like a balloon, where it can expand and contrast and keep things under constant pressure, there's no change in pressure, we call that isobaric. And then finally, like we said, an isolated system is where you can't change the energy within the system at all, and we use U as the internal energy of the system instead of the general E, which is just a general term for energy in general. So when we look at macroscopic variables that we use to define thermodynamics, we usually use a capital N for the number of moles and For example, we would sum over the number of individual components. So Ni components, we often sometimes put that as mole fraction of some component, etc. So again, just going back to introductory chemistry. And its corresponding, so this is an extensive variable, its corresponding intensive force is its chemical potential and this is where we spend a lot of time. This is where chemical thermodynamics comes into play right here. And will define a lot of equilibria, etc., or changing the number of moles and looking at reactions. When we think of the common mechanical properties, we start oftentimes by specifying that it's the external force into the displacement. But that's in one dimension. We can go from 1D to 2D, which would be its area and its surface tension. And then what I would say we're most familiar with in chemistry or biochemistry, which is actually talking about, 3D or three-dimensional space, the Cartesian space we live in, which is volume, and its corresponding force is pressure. So it would be the external pressure of the system. Now, in physics, we often introduce electromagnetism and talk about electrical work, magnetic work, etc. This gets sometimes introduced in electrochemistry as well. But really, a lot of the thing, and the name thermodynamics is given from, is looking at heat and defining what entropy is through the second law and corresponding it to temperature that we have a feel for. In introducing the first law of thermodynamics, the conservation of energy, we often start with work. And in your introductory physics courses, we would say that work is the external force times its displacement, or what I would like to say is that it's the external force into the change in its displacement, right? And so that's how we generally start to look at this. And we can, as I said, go up to 2 dimensions or 3. But even in 1 dimension, this gets very useful in biochemistry, and the book gives a really nice example, starting from kind of the basic physics of looking at the displacement, versus its spring constant here, and looking how you get these displacements. But it quickly moves to using atomic force microscopy to look at the displacement as you can look at biological molecules, in this case, looking at DNA, single and double-stranded DNA. So showing it here, I show one of the several examples they give using DNA, where you can look directly at the force applied versus how much it extends, and from that, get the amount of work done in these atomic force microscopies and relate that to energies, the internal energy of the system, and relate it to the thermodynamics of what's going on in these systems. As I said, you can move this to 2 dimensions, looking at the surface tension, of a liquid, for example, versus its surface area. And finally, what the book goes into in a fair amount of detail is looking at how you go from a linear force and its displacement to a 3-dimensional volume onto its pressure. And the book goes through that in significant detail so that you understand it. And one of the things I would say is critical here is to make sure we understand, as we go from the force over some, oftentimes it's called length, right? Or the force into some distance. These are kind of equivalent. It kind of gives a couple examples. For example, that force being gravitational, the mass on gravity, and then the change in the length or the change in the distance would be the height. So that's a type of work when we want to look at things, and they give several examples of this. As we showed the AFM example. But as you go to 2 and 3 dimensions, you will see that this force now over the area, which is the external pressure, into the change in its volume. But because this is in the same direction, this comes as the negative. And we think of this as it's coming from the system's perspective and the volume's decreasing. So we want to think of that as that from the system standpoint, which is what we describe here. So really what the first law of thermodynamics is saying is that we have a conservation of energy, and we can say that that energy, is either in the form of work or heat, right? And what I would say most explicitly is it's the infinitesimal change in the internal energy is the change which is path dependent, which is why I put this in the work and the heat, right? And this is what I would say is what I would write as the most general law, first law of thermodynamics, where now we can substitute in here what these work and heat terms looks like. Your book writes it, as such. So, as written here. But again, like what I would say is we'd like to use calculus here, where it's really, we're looking at the change in the internal energy, and it's path-dependent change in work, it's path-dependent change in heat. In other words, while this is a state variable, the internal energy, it's path independent, it only depends on the initial and final states that it's in. The work term itself is path dependent, and so is the heat terms. And you have to go along specific paths that are reversible to be able to change this general property. And that's one of the first critical things to get familiar with in thermodynamics. It's often defining these in terms of state variables so that we can look at path independence when it comes to some of these work and heat functions. And this is what I was mentioning earlier, which is we look at these from the systems perspective. And so we're going to define, work from the system's perspective as being positive if work is done by the system on its surroundings, if heat is given off by the system, etc. So, and then it goes through the general variables. And I mention this even though this is obviously something you've covered numerous times before, introductory physics and chemistry, and in almost every course, you've already looked at the units for energy pressure. I just want to emphasize that the number one mistake made on students on either quizzes or exams, etc., when working problems is not having the units correct, not converting units correctly, etc. So I would just strongly urge you to make sure you're very comfortable with kind of the units we use for energy, pressure, volume, temperature, heat capacity, etc. And your book goes through this fairly well, and there's tons of online resources. So that's really the first half of the chapter, introducing the first law. And the second part is taking the first law and looking at the heat component of it. So while we looked at the work component earlier, like for example, its mass, gravitational field, and its change in height, or we look at a force over some length or some pressure over some volume, mechanical type works. Now it goes and looks at the heat component of this. And the first thing it defines is that if you look at the change in heat and how that changes temperature, that's defined as the heat capacity. But it's very critical to keep in mind that you're usually keeping something constant here. So while we're changing the heat and looking at its effect on temperature, it's C is the general term used for the heat capacity, but we usually put a sub-variable of which variable we're holding constant during that process. So if we're holding pressure constant, we'll call that Cp, or the heat capacity at constant pressure. The molar heat capacity, it's usually at a fixed number of moles as well. Why, if we want to hold the volume constant, the constant volume heat capacity, and again, we often hold the number of moles constant in these things. And this shows, for example, how the heat capacity at constant volume and temperature are changing. So, for example, this one would be how the heat changes with temperature at constant pressure and number of moles. And this would be how the heat changes with temperature at constant volume and number of moles. Oftentimes the N is left out and it's just called a molar heat capacity. And this shows some examples, for example, of alanine versus glycine, two different amino acids used in peptides and proteins, et cetera, versus two different metals. And then several tables are given to show just how the heat capacity varies with, for example, molecular weight. The higher the molecular weight, in general, the higher the heat capacity, because there's more vibrational degrees of freedom. There's more molecules in different ways those can vibrate, et cetera. And it talks about some of the molecular underpinnings of this. And then why you get some things that are vastly different, even though they're the same molecular weight, et cetera. Like, for example, the famous case of water, which is covered in detail. It also introduces what I would say is the most common experimental aspect of looking at the heat, which is under constant pressure conditions. And it introduces, therefore, a variable, the energy variable that we look at under constant pressure. And the way I like to introduce this is to say we wrote down what the first law is. It's the change in internal energy is the change in heat plus the change in work, right? And what are these? Well, the change in heat, if we say that, we're not changing the number of moles, so, it's a closed system, and that we only have kind of pressure, volume, work in this case, so it's minus PdV, right? Well, then, this will, if there's no change in volume, then how the internal energy changes with temperature at constant volume, is, how the heat changes with temperature at constant volume. And like I said, constant number of moles. And that is CV, right? But we rarely work in chemistry or biochemistry under constant volume conditions. We almost always work under constant pressure conditions. So in a sense, what we want to do is flip these two variables here. And that's what enthalpy does. So enthalpy is a Legendre transform of the internal energy. So it's still the same number of independent variables, but it's just transforming which one are the independent variables. The simple example I love to give is something like if we had a function, versus x and y, right? We could give, for each one of these points, we could give the x and y coordinate of those points. And those are two independent variables that could define this overall function, right? But we could just as easily draw at each one of those points a tangent line and give it slope and intercept. So we could give two other variables that are independent, that are just as valid as the two we gave, as the two independent variables to define that function. So the same is true here. Enthalpy redefines the energy we want to look at and puts it in the other, in a dependent variable of temperature. And we can show this fairly simply by, if this is the definition, then this would be the change in internal energy plus the change in PV, right? So the change in enthalpy is U, and then by a chain rule, we can say this is PdV plus VdP, right? We just said that the internal energy is this, right? So this will mean that this is and then that'll go away, so plus V dP. So in a sense, we get similar to a similar equivalent to the first law, but instead of it being the change in internal energy, it's the change in enthalpy. And if we do it under constant pressure conditions, just like here, if we did it under constant volume conditions, then the enthalpy is just the change in heat. And because we often do things in biochemistry and chemistry at constant pressure, this is where this gets equated to heat so often. And in fact, it's one of the things I think that's always critical to come back and remind ourselves that this is true only for a closed system under constant pressure conditions. So, and so it's looking that this heat is only, happens under, when there is no change in pressure of the system. So, and then again, because this heat capacity is the change in heat over temperature, we can see that equivalence as well, right? And you can simply see here that some examples that if you take this enthalpy versus the internal energy, you plot it, it's the slope that's giving the heat capacity of these compounds. So, and this is quite a few examples are given in Tinoco's book, as well as a lot of data on different systems that we can use showing what some of the heat capacities and different thermodynamic variables are. They give a whole table on water and tables on numerous other things. Then it goes into looking at that enthalpy specifically under constant pressure conditions, for example, and how it affects in physical changes, like, for example, the melting or boiling of water, etc. And you can look at how those heat changes occur as you melt something or as you boil something, etc. So, and a good example here, just to keep in mind. So we're looking at the change. If the slope of this is the change in enthalpy with temperature at constant pressure, or the change in heat with temperature at constant pressure. And so you can just tell this has a shallower slope than this one, and it's because the heat capacity at constant pressure of liquid water is higher than that of solid ice. And then you can also tell that even over fairly large temperature ranges, that it's primarily the fusion and vaporization that dominate the heat effect, or it's the physical changes of water that dominate the heat effect more than how the heat changes over a fairly large temperature range when it's in one state of matter. We're also reminded in this chapter that enthalpy, so while heat itself can be path dependent, enthalpy is a state variable. It's path independent. It's an exact differential. It only depends on the initial and final states, and it means that way, if all we want to know is go from A to some products, we can take any path we want and we should get equivalent answers. And this is critical, and this is often why we look at state variables. We change the energy to look at the state variable for energy that makes the most sense for a problem we're working, is that we can go to whatever path where we know the experimental data for the system. So, for example, if we want to get from reactants to products, we can go through the heat of formation to the elements, then do the reaction, and then convert those elements back up to products. And this path, here, this path 1, 2 to 3 would be equivalent to the direct reactant product path. The other thing, which is where this gets used very often, is to look at reactions outside of just being done at room temperature. So for example, we want to know the reaction at, say, some high temperature, T2, but we can take the reactants, we can cool them down to room temperature, do that reaction, and then heat the products up to that higher temperature, and that path should be equivalent, right? So that we don't have to know how the delta H, we can in a sense separate it out, and we can look at how the enthalpy changes as you just change temperature, then as you change the number of moles, or you do the chemical reaction, and then you change the temperature of those products, right? And so it's critical, and this is in freshman chemistry called Hess's Law, and you can, there are very good Wikipedia pages, etc. And the overall thought is that enthalpy is a state function, it's path independent, and has an exact differential. Lastly, one of the things that's covered is to get towards the microscopic. In other words, to show that this can be taken to the extreme of basically breaking molecules up into its individual elemental or atomic components and then recombining them. And by keeping track of those dissociation energies, which are basically enthalpies, because we're typically doing this at constant pressure conditions, that we can then look at just the dissociation energies for all the different atoms bonded together, remove all those bonds, rearrange, and then form the bonds that form, and do that to look at it. And this has a huge relation to how we do things computationally oftentimes. And it talks about that a little in the chapter. Finally, one of the things I like best about Tinoco's book is that he does an excellent job at the end of the book of giving a summary of kind of all of the relevant points that make it really easy when you're trying to just find something quickly and working a problem or find some specific. And he even gives reference to exactly where it was, what equation it was within the chapter, etc. So hopefully this gives you a good overview of Chapter 2 in Tinoco, and we'll have some subsequent videos that cover some individual problems and individual concepts in this chapter. Thank you.